taking something that really was a fundamental new physics phenomena and taking that all the way to the point where it can change people's lives and have a real impact on both the state of Colorado and on the world economy. By making these lasers and making very short pulses of light, we found that we could manipulate atoms in a very precise way to allow them to radiate these X-rays.
If you take a guitar or a violin string and you pluck it gently, you can hear the fundamental tone. And if you pluck it harder, you'll hear higher harmonics of that sound. And if you pluck too hard, the string breaks. And it turns out that that laser that we invented to make an X-ray light bulb was just amazing at plucking electrons in atoms to where the electrons radiate not only the same color as the laser we use to perturb them, but also very high harmonics of that laser light. Our particular contribution was to figure out how to do that efficiently. And of course, this was with a big team of students. It took us 20 years to do.
CamLab started because we had developed a laser technology. One long weekend, I wrote up a document that told people how to make this laser, and it became viral before the word viral was really in widespread use. We started to supply this technology first in a very simple kit form, but things grew over the years, and now we have 40 people, and we are the most advanced laser technology company in the United States, I would say. What we're able to do now is make coherent laser-like X-rays using a tabletop scale apparatus. You can actually see neural activity in real time with these lasers and understand better how the brain works. But, people use these lasers in everything from chemical dynamics to looking at new materials to understanding energy flow in photovoltaics, understanding the combustion process to make the fossil fuels that we use burn more efficiently.
As you make the wavelength shorter, you can get a tighter and tighter focus. And so you can make crisper images. It turns out that that light can penetrate objects that are opaque to visible light. So you get a very nice probe, essentially, of the nanoworld.
We know what the possibilities are. We know where the challenges are to get there, and they're quite substantial. We are going to be developing the new technologies for at least the next 20 years, I would say. And the goal then is to spin out these new technologies and make them accessible and useful for a broad variety of applications.